Hello everybody, this is a video for 9.3 for the grade 12s. There we go. We're going to be showing you how to connect graphing rational equations um, to solving them and solving equations with them. So we'll start with this guy right here, and let's start by solving it algebraically. So algebraically, how do we solve this thing? Well, algebra means that we, of course, would like to isolate the x and solve for x. So let's start by moving that 1 to the other side of the equation. So we'll add 1 to both sides of the equation. Then from there, remember I need to solve for x. I don't want to know what 1 over x is. I want to know what x is. So I need to get that x out of the denominator. So I'm going to multiply both sides of the equation by x plus 2. On this side it cancels. And on this side I get 4x plus 8. So I would then get negative 7 equals 4x. So I'd get x is equal to negative 7/4. There we go. So there's the solution. Now, how do you solve this thing graphically? Well, graphically, what we do is we just take the equation and make two different equations, one for the left side of the equation and one for the right side of the equation. To make my life a little easier, I think I will move this 1 to the other side of the equation and say that that's the equation. Basically what I had after my first step here in the algebra form. So I'm going to graph 1 over x plus 2, and I'm going to graph, 4. And let's see what those two things look like when I graph them. So the first thing I'll graph is y equals 1 over x plus 2. So 1 over x plus 2 has a horizontal asymptote at negative 2. And of course it's, so here I'm graphing y1 equals 1 over x plus 2. So it has a horizontal asymptote at the x-axis. So, right, because there's no way y could be 0. And otherwise, it's basically my function y equals 1 over x moved 2 units to the left. So I know y equals 1 over x has a point right here. So if I move that 2 units to the left, I get that point. I know that there would be a point right here, right, 2, 1/2. So if I move that 1, 2 to the left, I get this point here. I know that there'd be a point on my parent function that's a 1/2 over and 2 units up. If I move that 2 units over, it's right here. And that should be enough, hopefully, to maybe figure out what my graph looks like. Maybe one more point. I know that if this is a 1/2 at a quarter, I'd move up 2 more spots, so that'd be maybe there. And good enough. Let's graph that. There we go. And I know there's another arm here, but I don't know that I really care about it because y2, let me use a different color, y2 is 4, right? Because I'm trying to solve this equation right here. So when you graph the left and right sides, wherever their x coordinates meet, or the x coordinate at the point where they meet, that must be your solution. So that would be my solution right here. Right? So that's it. That's the solution. And if you remember how I got this point here, it was because I knew that if I moved a quarter that way, I'd go up 4 that way. So this point is a quarter smaller than negative 2, or a quarter bigger, I should say, than negative 2. So if I take negative 2 and I add a quarter, I get negative 8/4 plus 1/4, and I get the answer that we got algebraically, which is 7/4. So that's how I would do that. And when it says in the notes to explain the relationship between the roots of the equation and the x-intercepts of the graph, you could say they are the same, but honestly, I didn't do it that way. What this note is talking about is if I had actually graphed this thing and that, but it was easier for me to move that over and graph this form instead. So I didn't kind of follow that method there. Okay? Next, let's try another one. So algebraically, let's solve it with algebra first. So step 1, I'm going to have to multiply both sides of the equation by x minus 1. So on this side, we get a cancel. But on this side, I'm going to end up with a quadratic. So that's going to be 2 equals x squared minus 3, oops, that's not what I was trying to write, minus 3x plus 2. The 2's cancel, which is nice. And then I can factor that. And then I can say x is 0 and x is 3. And I might do a quick check to make sure that they're right. Let's see, if x is 0, I get 2 over negative 1. And so that's 2 divided by negative 1 is negative 2. 0 minus 2 is negative 2. That answer works. If x is 3, I get 2 over 2 equals 1, and 3 minus 2 equals 1. So that answer works. Now let's do it graphically. So I'm going to graph two equations. I'm going to graph the left side and the right side and see where they run into each other. All right, so let's see what they look like. Okay, so for the first equation, y equals 2 over x minus 1. I'll just move over here. So y equals 2 over x minus 1. What do I know about that? Well, it has a vertical asymptote at x equals 1. So let's draw that. And it has a horizontal asymptote of y equals 0. So just indicate that by dotting off the y or the x-axis, since I can't cross that. And what else do I know about it? I know I have an x-intercept. So y is 0. So, oh, wait a minute, there is no x-intercept, right? I have a y-intercept of x being 0. And so my y-intercept is negative 2. And so I'll put a point there, negative 2. And then other than that, again, I know that this is the parent function y equals 1 over x. If you multiply your y values by 2, and then you shift every point 1 to the right. So I'm going to start with this point right here for my parent function. I multiply the y values by 2, and then I move 1 to the right. So that's that point there, which I kind of knew by symmetry had to be there, but okay. And then let's go to this point right here that would be on my parent function. 2 comma 1/2 times the y values by 2, so that would make it 1, and then move 1 to the right, so that'd be there. And then I guess I could go 4 1/4 would be a point. So 1/4 times 2 is 1/2, and then 1/2 moved 1 to the right would be there. So I'm getting a good picture now. I guess I could go this way. 1/2 2 would be a point, so the y value would get doubled to 4, and then it would move 1 over to the right. So there we go. We're getting something like that. This time I better graph the other side as well. Make the dot bigger when you miss it. And I know that it's by symmetry. It's going to be the same thing. So from this corner, I have to go 2 over and 1 up. So from this corner, I have to go 2 over and 1 up, 1 down. And from this corner, I go 1, 2, 3, 4, and I go up 1/2. So from the same corner here, I go 1, 2, 3, 4, and up 1/2. And I got this point by going 1/2 over and 4 up. So I'm going to go 1/2 over and 4 down. So there we go. There's my curve. Oops, I didn't draw that last line very good. Let me start that one over. Something like that. Okay, and in a different color, I'm also going to graph the equation y equals x minus 2, right? Because that's the other side of the equation, x minus 2. So what does that look like? Well, that has a y-intercept at negative 2, which is one of my solutions. And it has a slope, right, of 1. So I go 1 up, 1 over, 1 up, 1 over, 1 up, 1 over. And there's my other solution. I don't really need to draw anymore. I've got the two answers I'm looking for, there and there. And the x values here are x equals 0 and x equals 3, which are the same two numbers I got algebraically. Cool. So, little bit of an enrichment-y activity. We won't put these on the test, but they're fun to talk about. They're fun to think about. Asymptotes don't have to be horizontal and vertical. They can be oblique. Oblique is the word that means a line that's straight, but it's not at a horizontal or vertical. You might want to use the word diagonal line, but diagonal in math is a specific word that means the distance or a straight line between two vertices in a polygon, or an angle, a line that's at an angle of exactly 45 degrees if you're on a grid. So we like the word oblique. Oblique means not horizontal and not vertical. So if I were to sketch this thing, well, first thing I want to do is I want to say, can I factor the top and cancel this x plus 2? And the answer is no. There are not two numbers in the universe that times to make negative 4 and add to make negative 1. So I can't factor it. So you know what? I think I'm actually going to long divide it. I'm going to go x minus 2 goes into x squared minus x minus 4. And I'm doing this because I look at this thing and I really can't tell just by looking at it what kind of shape it is. It doesn't remind me of anything that I have in my memory banks to tell me what shape it is. Whereas on the last examples, the last two examples, as soon as I saw an equation like this, I went, aha, that's a split graph where the y value has been doubled and it's been moved 1 over. I knew that shape was going to look like these two arms here. When I look at this example, I have no idea what that's going to be, so I'm going to do some digging here, some investigating. How many x is going to x squared? Well, x of them. X times x minus 2 is x squared minus 2x. I'm going to subtract that. Negative x minus negative 2x is 1x. Bring down the minus 4. And then from there, I'm going to say, okay, well, what do I times x by to get to x? And the answer is, well, I times by 1. 1 times x minus 2 is x minus 2. And if I subtract that, x minus x is 0, negative 4 minus negative 2 is negative 2. And that's interesting. If y equals this mess here, then rewriting that answer nicely, y would equal the remainder over the denominator, so negative 2 over x minus 2. And I'm looking at that going, oh, okay, I know what that is. It's a split graph. It's got two arms and an asymptote, a horizontal asymptote of 2. But notice the remainder isn't a whole number. The remainder is x plus 1. Now, how do I think about that? Well, let me show you something. If I had the equation just y equals, you know, say, I don't know, 1 over x plus 3, and then there was a plus 1 here. Well, this, of course, I think of as the graph of 1 over x, where the shift is 3 units to the left and 1 unit up. But I also have to think that this thing has an asymptote, horizontal asymptote, of y equals 0. Now, why does it have that? Well, because 1 divided by x can't ever be 0, so I know that this thing can never touch y equals 0, so the x-axis is an asymptote. Now, how does that change? Well, the whole graph's been shifted up 1, so the asymptote for this graph has also been shifted up 1. And another way to think about it is, if I try to figure out what y can't be to find the horizontal asymptote for this, well, this fraction, this whole thing, can't ever be 0. Again, 1 divided by anything, no matter what it is, can never actually be 0. So if this fraction can't be 0, y can't equal, y can't equal 1. So my horizontal asymptote is y equals 1, which is what I thought when I realized, oh yeah, the parent function just got bumped up 1. But now you can see algebraically why the horizontal asymptote is y equals 1. So when I graph this thing, it would look like this, right? It would have an asymptote there, and an asymptote 1, 2, 3 here, and it would be, okay, not my best drawing, but you get the idea. Over here, look at this one, and think about what's going on. This fraction, again, can't be 0. Negative 2 divided by anything can't be 0. So in this case, my asymptote for y is that y can't equal x plus 1, right? If this can't be 0, then y can't ever equal x plus 1. And y equals x plus 1 is linear, but it's not horizontal. So it's not a horizontal asymptote. It's an asymptote where I have, let's see, y equals x plus 1. Did I do this right? X plus 1? Let me double check my answer here. X goes into x squared, x times, so minus 2x. Negative x minus negative 2 is 1. Yeah, I think I did it right. Okay, sorry, I was just doubting myself. All right, so anyway, like I said, I have an asymptote of y equals x plus 1. So at plus 1, and then going that way forever, I have a line that my graph can't touch. So, make that a little smaller so I can fit the whole thing on here. So let's see, let's run through the jungle here. What do we know about this? We know that we are dealing with y equals negative 2 over x minus 2 plus x plus 1. So my non-permissible value here for x is, of course, 2. And that doesn't get canceled or anything, so that's a vertical asymptote of x equals 2. So let's draw that on there too. X equals 2. There we go. And then we're going to say, okay, so what's my x-intercept? All right, well, x-intercept's at when y is 0. So if I have 0 equals, let's go to the original equation, probably easier. 0 equals x squared minus x minus 4 all over x plus 2. If I times both sides of the equation by x plus 2, I get 0 equals x squared minus x minus 4. And I'd have to run that through the quadratic formula. And I did that, and I got x equals 1 plus or minus root 17 over 2. And if I just roughly estimate that, root 17 is about 4.1 because the root of 16 is 4. So that's going to be somewhere close to 1 plus 4 over 2. So 5 over 2 is like, 1.5, is 2.5. So it's going to be around 2.5, maybe in a bit. And then what if this was a negative? Then this would be, again, around 1 minus 4, which is negative 3. So it's going to be around 3 halves, which is 1 point, it's going to be negative, though, negative 1.5. But it'll be a little bit on the left. No, wait a minute. Which way would it be? I gotta think about that. This is bigger, 6.1. So it'd be actually maybe a little like negative 1.55 or something like that. So that's the 2 points I'm going to put for my x-intercepts. Around 2.5, but a bit past it, and about negative 1, there you are, and a half, but maybe a little bit past it. And okay, so interesting way for this thing to kind of start turning out. So what kind of a graph are we getting here? Well, turns out that this thing is going to look something like this. First of all, its x-intercepts again are around approximately 2.55 and negative 1.55. The y-intercept, the y-intercept is, what was the y-intercept going to be for this thing? If for y-intercept, this is me finding the x-intercept. For the y-intercept, if I plug in zeros for the x's, I get negative 2, right? Because I get negative 4 over 2. So I get a y-intercept of negative 2. And let's see, is that going the way it's supposed to be going? What? Oh, I see what I've done. Oh, I knew this was looking goofy. What's my mistake? Do you see it? There it is. The non-permissible value is 2 is wrong. The non-permissible value is negative 2. So my vertical asymptote is x equals negative 2. So it should be over here. There we go. There we go. There. And I think I might have my, I don't know if I have that right or not either. Let's see. So what's the, this dot was just me trying to find the asymptote. That's not a dot on the graph. Let's see. We might have some other issues with this graph. I might have to fix this. Let's go back and see if I can fix it. What have I done wrong? Oh, there we go. Yeah. That should be a plus. There we go. Okay, I'm going to have to redo this divide. My apologies. And okay, so that's going to put everything off. Well, okay, that's an x squared plus 2x, and then when I minus, I get negative 3x minus 4, and then I'd put a minus 3 there. That's going to give me negative 3x minus 6, and when I minus that, I'm going to get 2. Okay, so that means that 2 is my remainder, not negative 2. And this is not x minus 2, it's x minus 3. Oh, that's going to put everything off. And my answer is x minus 3. Ugh, oy, 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 oy. So y cannot equal x minus 3, not x plus 1. There we go. Now we're fixed. The x-intercept's still in the right place because it's that. The y-intercept, however, I used the original equation, so I've got that right. So the x and y-intercepts are right. But I have the asymptotes in the wrong place. So let me just redraw the asymptotes really quick. Guess I should have worked out a key before I started this. There we go. Okay, so my non-permissible value is, in fact, this is a plus 2, this is a 2, and this is an x minus 3. Okay, so my non-permissible value is, in fact, -2, which means my vertical asymptote is x equals -2. My y-intercept I found was -2, which I already drew. X-intercept I found. Now, so my horizontal asymptote, I don't really have one. Point of discontinuity, I don't have one of those either, but I have an oblique asymptote. So the oblique asymptote is this: y cannot equal x minus 3. So it's y equals x minus 3. So let's draw that asymptote better. So it's x minus 3, so it goes through -3, which means, and it has a slope of 1, if you're wondering how I'm making this line. So there, that's the line that we can't cross. And the vertical asymptote, again, happens at -2. So my graph is going to go through these 3 points here. And then I know that down here it's going to actually do the same thing. So it's going to have an arm going that way. But my grid doesn't have enough room for me to show it. And to actually find the domain and range for this, well, the domain is fairly easy. There's only 2 x numbers that we'll never actually have. You'll never have this x number here. So x cannot equal, that'd be 3. And you can't have this x number here, so -2. Besides that, you could have any real number you want. Now, range is actually something you can't do using grade 12 regular math. To figure out exactly where this point is and where that point is, so you can find the range, whereas y would be anything bigger than this value and smaller than that value, that actually is something you learn how to do in introductory calculus. So that's it. That's how those work. I'll go through the next one. Maybe pause it and try it yourself if you'd like to see if you could do it. And then I'll run through it, and hopefully I won't make as many mistakes as I did in the first one. Okay, so pause the video if you want to try it again, or try it for yourself. All right, how did that go? So the first thing I want to do is I want to, again, long divide to figure out what kind of shape I'm dealing with here. So y equals, and I'll rearrange this like so that it's in the right order, and then I'll go x minus 2 goes into -x squared plus 2x plus 3. Let's make sure I didn't recopy the question wrong like I did last time. Nope, we got this right this time. Okay, x gets times by -x to get me to -x squared, making that plus 2x. And then when I subtract that, I get 2x minus 2x, which is nothing. I bring down the 3, and then, oh, that's it. That's my remainder. So my answer for y, my other way to write the equation, is the remainder of 3 over x minus 2. But my solution isn't a whole number, it's x. So this one doesn't give me a chart, does it? No, it doesn't. Okay, so I'm just going to start rattling off all the stuff I need to draw this thing. So does it have a vertical asymptote? And the answer is yes, x equals 2. Does it have a horizontal asymptote? And the answer is no, right? There's no number I couldn't make for y here. So none. Except, of course, for the fact that there is a whole bunch of y numbers that I can't touch because y can never equal -x. So my oblique asymptote is y equals -x. Okay, so let's start drawing stuff. Y equals -x goes through here and here, right? So it's just the diagonal line through 1, 1, 2, 2, 3, 3, and its negative companions. There we go. So that's the line we can't touch. I didn't draw this very good. It's supposed to go right through the origin. You get the idea. All right, do we have any x-intercepts? If y was 0, I'd have 3 over x minus 2 equal, minus -x, or minus x, I should say. Move the x to the other side, and I get 3 over x minus 2. Times both sides of the equation by x minus 2, I get x squared minus 2x equals 3. So I get x squared minus 2x minus 3 equals 0. And that has zeros at 3 and -1, right? So x-intercepts, so this is me finding my x-intercepts. And I found them at 3 and -1. 3 and -1. There we go. Do I have any y-intercepts? My y-intercepts happen when x is 0, and that's going to be 3 over 0 minus 2 minus 0. So I have 3 over 2, so that's negative 3 halves. So y is negative 1 1/2. That's that point right there. And that, that ought to do it, I think. I can see that I have, let's get the vertical asymptote down. I didn't do that yet. I have a vertical asymptote here at 2. And as you can see, I'm going to have some sort of curve that's kind of heading this way. So as with any asymptote, you're kind of heading towards it. And something like that maybe, and then the other arm would be going the same way. So something like that. And there we go. That's how you do oblique asymptotes. Like I said, everything from examples 1 and 2 on oblique asymptotes won't be on the test, but there could be very much a question like these first 2 examples where you have to use the solving techniques. There's one last thing that I didn't do yet. It did say to actually solve this algebraically as well. So let's see, if I solve this thing algebraically, let's see, so solving this thing algebraically would be, let's see, I'll add x to both sides of the equation, 3x minus 6, I'll times, you know what, I'll divide both sides of the equation by 3, that makes my life a lot easier, and then I'll times both sides of the equation by x minus 2, and that gives me the equation x squared minus 4x plus 3, which solves nicely to x minus 3, x minus 1. So x equals 3 and x equals 1. And then it says use the sketch graph to solve this equation graphically. So the equation that I have graphed is here, right? This thing is what I graphed, right? Right? 3 over x minus 2 minus x. And if I graph now the line 2x minus 6, I should hit it at those 2 x points. Let's see how accurately that's going to happen. I don't know if that's going to happen too accurately, but we'll give it a try. 2x minus 6 goes through minus 6 and it has a slope of 2. So up 2 over 1. There we go. I hit it there. And then up 2 over 1. And then up 2 over 1. Boom. Hey, that's not too bad. We got it. So there it is. X is 1 and x is 3, just like the algebra told me. So there we go. So again, we won't be asking you to graph things with oblique asymptotes, but the strategy I just used there, where I graph a rational and then use it to solve an equation, that definitely is something we'll test you on. Thanks for watching.